Okay, so in this section, we're going to look at an integration technique called integration by parts. So you have to be able to apply integration by parts as needed. And if you remember back when we first learned how to integrate, we looked at the power rule, which told us if you wanted to integrate a polynomial a piece at a time, that you would take the power you saw, you would add to it, add 1 to it, and then divide by the new power. And that got us through our basic examples, but then we started running into examples where that just wasn't working, even if we FOILed everything out. So then we looked at U substitution. That was an integration technique, and we worked quite a bit with it. This is another integration technique, integration by parts. We'll work through some examples so you can see when to apply it, and that will be the tricky part. That's why you need to practice so that you can recognize when you see a problem whether you should do integration by parts or whether you should try some other technique. So, through substitutions and the product rule for differentiation, so we're going to look at our product rule for derivatives. That's where we get the integration by parts formula. So, looking at product rule, if I want to differentiate the product UV, well then that's first times derivative of second plus second times derivative of first. But if I go back and really look at this notation, it's saying I want to differentiate UV with respect to x. That's why they put that d by dx, the dx part down there. So the v prime that I see is really dv dx. And the u prime that I see is really du dx, if I switch over to that notation. Well, that notation is helpful to us if we want to integrate. So now if I take that same formula, that same product rule derivative formula, and I want to solve it for the left side, get uv just by itself. I want to undo the derivative. Well, to undo the derivative, I'm going to integrate. So I'm going to integrate the left side, the d by dx of uv, and I'm going to integrate with respect to x, so I'm going to put the dx there. Get rid of this extra little piece. So then that equals, and I'm going to integrate on the right side a piece at a time, the u dv dx, but I want to integrate that with respect to x, so I'm going to put dx there, plus, and then I'm going to integrate v du dx, but again, I want to integrate with respect to x, so I'm going to put the dx there. And by looking at that notation, you're more easily able to see that over on the right side, those dx's will wipe out. Well, then if I come and look over on the left side, if I have integrated the derivative of uv, I expect to get uv back out. Yes, there would be plus c's that are involved because I don't have bounds here. We're just going to leave that off as we work through the formula, kind of like you saw in Chapter 5 when we did differential equations. You're able to lump all of those plus c's together, and for the sake of the formula, they don't include it in there, so we're just going to leave that piece out. And then over on the right, we are left with the integral of u dx plus the integral of v du. Okay. At that point, if you scroll down a little bit on your page and look, your integration by parts formula is solved for the integral of u dx. Sorry, I miscopied that. The integral of u bv. I just miscopied from the line above. So if you look down at the formula below, it's solved for the integral of u dv. So we want to solve for this integral. Okay, if we want to solve for this integral, then I need to subtract over the integral of v du. So on the left, I would have uv that was already there. But then I want to move one of the integrals from the right side. So I'm going to subtract the integral of v du. And that's going to be equal to what I was interested in, the integral of u dv. I realize that this looks a little strange because it looks like our letters aren't matching up as far as integrating v du and u dv. Usually those letters match. And they really do once we work problems, because as you start to take a look down here, so then this is the integration by parts formula, but they add a piece to make that make sense, that u and v are functions of x. U and v are standing for something more complicated. They're a replacement for something more complicated. So you'll see that when we work problems, we will actually be integrating with respect to the same letter all the way through. That'll actually work out nicely. Okay. I just wanted you guys to see where the integration by parts formula comes from. And all it's coming from is our product rule for derivatives. Integrating both sides to undo that, doing some algebra work to move things around, and you get this formula that you see in the book, or that you see in this notes packet. As far as memorizing that the integral of u dv is equal to uv minus the integral of v du, that's not super important. The process itself is super important, and I will show you a way to lay out your work so that you can remember what you're doing without getting so hung up on, is this supposed to be v or is this supposed to be u, and not understanding that piece. So one thing that you need before we proceed is you're going to have to pick out from your original problem, because our original problem is going to be over here on the left. You're going to have to pick out from your original problem what the u is going to be and what the dv is going to be. So instead of just regular u sub like you're used to, now you're going to substitute in and let u equal something and let dv equal something. Well, it's helpful if you choose u as something that's going to get simpler when you differentiate. And it's helpful if you choose dv as something that's going to get simpler when you integrate, because dv is a differential, and as we work with those, we integrate both sides. Okay. Usually, that means your more complicated piece is going to be the dv, and it's going to get better as you integrate. However, you have to make sure that whatever you pick for dv, that you actually do know how to integrate it. It can't be so tricky that you don't know how to find the integral. So let's start working some examples. All right, we need to integrate x e to the x dx. And this is a product, and if you try regular u sub, it's not going to get you anywhere. So if we want to try integration by parts, because we see that it's a product, we need to pick what u is going to equal, and then we need to pick what dv is going to equal. If I were you, I would write it down exactly like I have it, sideways like this, because it'll give you a good visual to remember what you're supposed to do. So I'm going to differentiate u. I want to pick it as something that's going to get simpler as I go. My choices are between this x that I see and between this e to the x that I see. If I pick x, the derivative of x is 1. That definitely got simpler. If I pick e to the x, derivative of e to the x stays e to the x. Similarly, if I pick e to the x and I want to integrate it, that's going to stay e to the x as well. So it doesn't really matter where I put that part. But since I have to eventually integrate this dv, I don't really want to integrate x, because then it's going to turn into x squared over 2, and that didn't get simpler, that got worse. So let's pick u as x. Let's pick dv as the rest of what I see. So e to the x dx. You're starting with your original problem, x e to the x dx. And you are assigning all the different components to either fit under u or to fit under dv. So the x we have put over here under u, and then that leaves the e to the x dx that we've put over here for dv. Now, we were really just picking what dv was on its own. I'm going to get rid of that integral symbol. Just when you do that, you need to realize that you are going to eventually integrate dv, so you want to think about that. So now, I want to integrate both sides of this piece. I want to integrate dv so that I get plain v back out. Integral of e to the x is e to the x. Yes, there is a plus c. That will come later as we do our work. I talked to you about that on the very first page. I want to differentiate what I have for u, but I want to do it just in the same sense that I do for u sub. So for this first example, I'll write it out the long way. Du dx is equal to 1, so that means du is equal to dx. But eventually, you'll be able to just go straight to u equals x, so du equals dx. Again, your guide, I wouldn't necessarily highlight this on your paper, but your guide is that u gets simpler as you differentiate, and then dv gets simpler as you come back through and integrate. Okay, I'm going to take that part off. All right, now we're trying to fit into the pattern that we had. Again, you're not going to write this all the time, but since it's our first time, the integral of u dv is equal to uv minus the integral of v du. Well, I have the integral of u dv. That's the integral of x times e to the x dx. I have that. Equals, and now here's where the formula comes in. It tells me that it equals u times v. And if you write your work in this way, it gives you a visual for how to work the next component. I need to take u times v, so x times e to the x, minus, and then I need to integrate v du. v du is e to the x times dx. So the integration by parts formula tells me that the integral of u dv, which I can see how that works in my problem, is equal to uv, and I went back and substituted that, minus the integral of v du, and I went back and substituted that. Again, I wouldn't keep all that highlighting. Now I'm left with something that I'm able to work out. This piece over here, e to the x dx, that's an easy integral. And the other component, the uv, I don't have to do anything with that. So I can just leave it. So this is equal to x e to the x minus, and the integral of e to the x is e to the x, and this is the point where we put in our plus c. So my original problem is equal to this. It's definitely different. We haven't seen anything like this up until now. But if you wanted to check that you did it right, differentiate what you have, and you could see that it works. So find the derivative with respect to x of x e to the x with product rule. Take off e to the x when you get done, and then add c. Well, when you differentiate the c part, that's going to go to 0. And check that if you work it all out, you're going to end up with x e to the x. Check and see that that comes out to be true. Okay, so that was a product, and typically integration by parts works really nicely for products if you're not able to do regular u sub. So as we go to the next example, we see that it is also a product, and I want to take my original problem, my x squared natural log of x dx, and I want to separate out all the pieces to choose a u and to choose a dv. When I choose u, it needs to get easier as I differentiate. When I choose dv, it needs to get easier as I integrate. Well, in this particular case, if I split up my product so I can tell what I have, the x squared part, it definitely gets easier as I differentiate. It would become 2x. As I integrate, it's going to be x to the third over 3, so not easier, it got worse. However, if I start to look at natural log of x, if I differentiate natural log of x, I get 1 over x. Not bad. Natural log wasn't bad either. If I try to pick natural log of x over here, don't write anything for a second. If I try to pick natural log of x for dv, we don't know how to integrate natural log of x. So I can't choose ln of x as my dv because I can't integrate it. That's a problem. So I need to make sure that whatever I pick for dv, I'm actually able to find its integral. So that means in my problem that u is going to be natural log of x because I know how to differentiate it. And so by default, by process of elimination, dv is going to be x squared dx. I have to account, just like for u sub, for all of the different pieces. So dv is turning into x squared and dx. And then u on its own is turning into natural log of x. Okay, now I need to differentiate the u. So du is 1 over x dx, just like we would do for u substitution. And then over here with the dv, I need to integrate both sides. So v is equal to x to the third over 3 plus c. But actually, just like we saw in the last problem, we can wait to do our plus c until the very end. Okay, so now I'm going to turn, again, if you need to write it for a little bit, the integration by parts formula, the integral of u dv is equal to uv minus the integral of v du. Eventually, you won't need that part anymore. You'll just understand the process. But I'm going to line up all of my components. So my u was natural log of x, and then my dv was x squared dx. So that integral is equal to u times v, so it makes a diagonal where you multiply those. And usually we'll put like the little pieces in front, so we would probably say 1/3 x to the third and then ln of x, because you can multiply in whatever order you want. So 1/3 x to the third times natural log of x, that's uv, minus the integral, and you go straight across, of v du, x to the third over 3 times 1 over x dx. That was u times v, as I had up here at the top, minus the integral of v times du. And again, like I was telling you at the beginning, it looks like your letters don't match up. But once you see that u and dv are really standing for something else and you get everything plugged back in, the letters really do match up as you integrate. So I can just carry this down. This will be 1/3 x to the third natural log of x minus, and as we're going to integrate, it's going to help us if we clean this up a little bit. So x to the third over x is really x squared. And when we integrate, we know we can move constants in front. So I could move this to be the integral, or sorry, move this to be minus 1/3 the integral of x squared dx. And then once I actually integrate for that last step, that's where we put in our plus c. So I get 1/3 x to the third ln of x minus 1/3 x to the third over 3 plus c. And I just need to clean up my final answer. It's up to you how you want to do this. If you just want to multiply everything out, you'd have 1/3 x to the third natural log of x minus 1/9 x to the third plus c. Or if you want to kind of take a look at that stage and see some stuff in common, maybe they do take out a third and an x to the third. And then they would have natural log of x minus just 1/3 and then plus c. And that's just going to depend, like we've talked about, on multiple choice. You have to match up to what you're seeing, but on show your work, you can kind of choose how you want to leave your answer. So again, we saw integration by parts is something nice to try when regular U substitution just doesn't really get you anywhere. And you have a product. Okay, let's look at a couple more like that. And if you want, you could try U substitution for these on your own for a little bit and see that it's not really getting you anywhere, and that's why we need this other technique. So if I have x squared and cosine of x that I need to split up and decide, I need to decide what's going to be my u, and I need to decide what's going to be my dv. U needs to be something that gets easier when you differentiate. And dv needs to be something that gets easier when you integrate. Ideally, it's nice if u could be x squared. But if that's the case, then dv is going to be cosine of x dx. You have to make sure that you can integrate cosine of x, and we can. We're going to get the sine function. The reason that it's nice to have x squared as your u is because then when you take du, you get 2x dx. You've knocked the power back by 1. And we'll see this. Sometimes you have to repeat the integration by parts process. So it's nice if you can let the u be your x squared or x to the third or something like that, where you knock the power back every single time, because eventually then you would get to where you differentiate and just get a constant. And that's easy to work with. The dv part has to be integrated on both sides. So I get v equals sine of x, because derivative of sine is equal to cosine. And so now I'm not going to write out the whole formula like they give you. You can if you want. But x squared cosine x dx is equal to uv, so x squared sine x, minus the integral, and you go across, of v du. So sine of x times 2x dx. Okay, so I have x squared sine of x minus, we can move the 2 in front, and then have x sine of x dx. But again, I have a product, and regular u sub, if you want to try it, doesn't really get you anywhere. So I have to do integration by parts again on this piece. So when I choose this time, it's going to be nice if u can be x. So then to match up all the other pieces, dv has to be sine of x dx. You're going to differentiate the u, so du is equal to dx. I told you that's nice if you have to repeat the process, because eventually you just get down to a constant, du equals dx, or du equals 5 dx, or something like that. For dv, you have to integrate. So v is equal to cosine of x, and double check about your negative signs. Derivative of cosine is negative sine, so that means the integral of sine is negative cosine. Okay, so I can now do integration by parts on just this component. Okay. And you want to leave it within the problem, so it'll become uv negative x cosine of x minus the integral of, and go across, v du. So negative cosine of x dx. I'm going to change that to a plus, my double negative. And then thinking about integrating cosine of x, I can do that. The integral of cosine of x, it's either sine or it's negative sine. The derivative of sine is cosine, so the integral of cosine is sine. And now we can do our plus c. So we have negative x cosine of x plus sine of x plus c. That was just this red portion, though. So I need to have the rest of the problem. I need to bring that down. So I have x squared sine of x minus 2 times everything I came up with. I can leave the plus c out at the end because, as we've talked, if I want to distribute and get negative 2c, I can call that some other c value. I can lump it all together. But I am going to have to distribute the negative 2 to my other components. So I will get x squared sine of x plus, because I have a double negative, 2x cosine of x minus 2 sine of x, and then plus c. So this was a case where I had to use integration by parts a couple of times, because the first time still left me with x times a trig function, and I wasn't really able to get anywhere. Okay, so hopefully at this point you've started to see integration by parts is really, really helpful when you have products, and that's because it comes from the product rule for derivatives. Now I want to make sure we go over one that has bounds, so you know how that works. So again, it's a product of x and a trig function, so a good choice for u is going to be the x, because du is just dx. That got simpler really quickly. So then that leaves dv to be the other components of the integral. So coming back over to the original problem, dv is whatever's left if you've already chosen u to be x. So dv is sine of x dx. And then we always integrate that because we need to figure out what v is. So v is equal to cosine of x, and then check your signs. Derivative of cosine is negative sine. So that means the integral of sine is negative cosine. Okay, so now I have the integral from 0 to pi of x sine x dx is equal to u times v, so negative x cosine of x, minus the integral of v du, so the integral of negative cosine of x dx. And I'm going to go back and change my double negative to just be a plus. And now I'm also going to go back and talk about the bounds on the original. The bounds were 0 to pi. I have to make sure that I apply those bounds to the first part of integration by parts, to the negative x cosine of x. And it's your choice if you want to bracket the whole thing. Sometimes in this notation, we'll just bracket that last little piece, and that shows that we're going to apply 0 to pi to everything that came on the left of those brackets. And then I also need to put my bounds 0 to pi on the part that I have left to integrate. Okay, so the bounds work just like they have for any other integration piece. You always do top minus bottom. So negative pi times cosine of pi minus negative 0, which doesn't make any sense, that zeroes that out, times cosine of 0. Okay. Okay, excuse me, I had to pause for a minute. So I've plugged in the bounds on that first component, and then I need to come back over here and deal with the fact that I need to integrate. So the integral of cosine is sine. Let's check that. Derivative of sine is cosine, so that works out. But I have bounds on that from 0 to pi. So when I evaluate that piece, that's going to be sine of the top, so sine of pi, minus sine of the bottom, so sine of 0. Okay, so as I go through, I am left with negative pi times cosine at pi is negative 1. And then plus 0, because this zeroes the whole thing out. Even though cosine of 0 is 1, 1 times the 0 that I see in front there zeroes that out. Sine of pi is 0. and sine of 0 is 0. So those pieces don't end up contributing. So the only thing that I'm left with once I clean up is pi. Just like for any other integrals that had bounds, if you have an integral with bounds, most likely then, as long as your bounds are constant, you're going to end up with a number for your answer. But the tricky part is to make sure that you apply the bounds to this first part, to the UV part, as well as to the actual integral part. The bounds apply to both components. Okay, so we've seen integration by parts for several products now. We've hopefully gotten better at picking U and dV. Now we need to look at some tricky examples, and that's the last two that we'll take a look at. So we need to integrate natural log of x dx. But we've talked about we don't know how to integrate natural log of x. We know how to integrate 1 over x dx. That gets us natural log absolute value of x plus c. But up until now, we don't know how to integrate natural log of x dx. Okay? We're going to be able to do that with integration by parts, but up until now, we've seen it working for products. X times some trig function, x times e to the x squared times e to the x, something like that. Right now, all I see is natural log of x dx. Well, I have to interpret that as a product, natural log of x times dx. It's a product, I just have to think about it a little bit differently. Since I don't, so it's a product, we're going to apply integration by parts, or we're going to try to, because we don't know what else to do. Since I don't know how to integrate natural log, I cannot pick natural log of x to be my dv part. So that means, just by default, that the u needs to be natural log of x because I know how to differentiate. du is 1 over x dx. But then dv, well, by process of elimination, the only component left of my product is dx. So I integrate both sides. The integral of dv is v, the integral of dx is x. Okay, so integration by parts formula, it tells me that natural log of x dx is going to be equal to, and now I use the arrows that I've been talking to you guys about, u times v, so natural log of x times x. It might help you to use parentheses here. We're only taking natural log of that first x. Or it might just help you when you rewrite your answer to put the x in front, x, natural log of x, so you don't get it mixed up. Integration by parts formula tells you to take uv minus, and then go across, the integral of v, so the x, du, times 1 over x dx. uv minus the integral of v du. Okay, well if I clean that up, the x's here cancel because this is x over 1 times 1 over x. So I'm really integrating 1 dx. We can do that. So I end up getting x natural log of x minus the integral of 1 is just x. The integral of 1 dx is just x. And then you can put your plus c at the end. So you must use integration by parts to integrate natural log of x. We just have to look at the product in a little bit different way and look at natural log as one part of the product and then dx as my other part of the product. Okay. Last one, we want to look at integrating secant cubed. And if you want to try splitting it apart and trying to do u sub. You definitely can, but if you let u just be regular secant, the derivative of that is secant tangent, and I don't see that sitting there, so that's not a good option. U sub just isn't working. So I need to be clever and decide how I want to split this up so that I have something to integrate and something to differentiate. And it turns out in this particular one, we want to look at just a secant of x, and then we want to look at the secant squared part of x dx. It's not nice if you try to let, because we're going to pick a u and a dv. If you try to let u be the whole secant cubed, that derivative is really ugly because you have chain rule components. Since you have something to the third power, you have to deal with the power rule for that. But then you also have to deal with the derivative of the inside, which in this case would mean differentiating secant. And so you get secant tangent. It's just kind of messy. So what we're actually going to do is let u be just one of the secants. We'll let u be secant of x. And then that leaves our remaining part, the secant squared x dx, to be our dv. And that actually works out really nice. Hopefully that's looking familiar to you. The derivative of tangent is secant squared. So that means I can integrate secant squared really easily. So going over to the dv part, v is going to be equal to tangent of x. So then du, because I need to differentiate whatever is u, derivative of secant is secant tangent. So secant x tangent x dx. And then I am integrating secant cubed of x dx with integration by parts. So that is equal to uv, so secant x tangent x, minus, and then I need to integrate and go across, the integral of v du. So tangent of x times secant x tangent x dx. So I really have secant x tangent x minus the integral of tangent squared x secant x. Okay. And for this one, so to try to figure out what to do in order to integrate what I have left, don't write for a minute. You just need to start thinking through if you know what to do. So maybe I let u be secant x, but then du is secant x tangent x dx, and I don't have those components there, so that's not really helpful. Well, maybe I let u just be one of the tangents, tangent of x, because if I let it be tangent squared, that derivative is going to be really ugly, and I don't see it there. But du, if it's tangent, is secant squared x dx, and I don't see that either. I don't have enough of them. I just have one secant. So u sub there didn't work. I could try integration by parts again, and you're more than welcome to do that. But it's kind of ugly. So trying integration by parts multiple times is really nice if one of your pieces is like an x or an x squared, because then you just knock the power back a few times until you're left with a constant. But integrating your trig functions, you just keep getting more trig functions. So trying to do integration by parts several times with those can kind of just leave you running in circles. So if we don't want to try that, another thing that we haven't tried is just being creative and trying to use some identities and things that we know. So coming from the fact that sine squared of x plus cosine squared of x is 1, I've shown you how to get the other identities that go with it. We end up with 1 plus tangent squared of x is equal to secant squared of x. So if I solve for tangent squared, tangent squared of x is really secant squared of x minus 1. And the reason that that's nice is just because then at least my trig integral all involves the same trig function. So I now have secant x tangent x minus the integral of secant squared x minus 1 times secant x dx. Just making the replacement for tangent squared. I'm going to go ahead and distribute in there so I can see what I'm working with. So this would really be secant x tangent x minus the integral of secant cubed x dx plus the integral of secant x dx. Just distributing in and splitting it apart into pieces. Well, one piece I can figure out. I know how to integrate secant of x dx. That's one that I'm supposed to have memorized. So if I know how to integrate that, but then I'm back to a trig function with a power, and we talked about how annoying that is, I actually want you to recopy your original problem. Your original problem is secant cubed x dx, that we want the integral of that. And now I want you to notice that it's actually showing up on both sides of my problem. And it's not showing up with the same sign on both sides. On one side it's positive, one side it's negative. So they're not going to cancel each other out. What I want to do then, if I know how to integrate just secant of x, I can figure that out. I'm going to add the integral on the right, the negative secant cubed of x dx, this integral. I'm going to add it over to the left. So I'm going to get 2 times the integral of secant cubed x dx is equal to secant x tangent x plus the integral of secant x dx, which I know how to find. So that integral is the natural log of absolute value secant x plus tangent x, and then I can put in my plus c. And I still have my secant x tangent x. And that's equal to 2 times what I started with. Well, if I really want to solve for what I started with, then I really just want to move this 2 that's multiplied. I can do that algebraically. I can just divide both sides by 2. So I could have all of this over 2 so that it cancels, and I could have all of this over 2. That's kind of annoying to write, so most likely you'll see the answer given as integral of secant cubed x dx equal to 1/2 times, and I'm just going to do the whole quantity, secant x tangent x plus natural log absolute value secant x plus tangent x. I'm going to close my parenthesis, and then I'm going to do my plus c. So this is tricky in the sense that as we worked it out and we tried to figure out the integral piece, our integral piece was kind of ugly. And U sub wasn't really working on it. So we did some trig identities to get it worked down. And as we did that, we started to notice the original problem. So the original problem was on the left, and it started to show up with a different sign, in the sense of plus negative, on the right. So we lumped them together. We added that integral on the right side, we added it back over to the left side so that we had 2 of what we started with. And then once we got everything worked out, it was easy to get rid of the 2. We could just divide both sides by 2. So your trickiest ones are when it's not quite clear whether you should apply integration by parts or not, like in our natural log example, it wasn't quite clear that that was a product really. We had to think about it a little bit differently. And then it's also tricky when you get going and you start to see your original problem and you kind of think you're not getting anywhere. As long as you have one that's positive and one that's negative, you really are getting somewhere. You can add them to the other side and keep working. Integration by parts definitely takes practice. So you need practice at picking the U and picking the dV and working it all out. The other tricky part is the bounds and just making sure that you apply the bounds. If we look back on the last page, making sure you apply the bounds to both the UV part and to the integral that you have to find. Okay. That's it for the technique. Like I said, it just takes practice from here. So get working on that, see how it goes, and see what you need help with.